All right, good morning, everyone. We're going to get started. Welcome to Shell on Earth, from browser to system compromise, with Matt Malinyawe, Jazel Spellman, and Abdul Hariri. Before we begin, it's a reminder to please stop by the business hall located in Bayside AB to visit all of our vendors. And there's a welcome reception there tonight from 5:30 to 7. The Black Hat Arsenal is in the Palm Foyer on level 3. And remember to join us for the Pony Awards in Mandalay Bay, BCD, at 6:30. And please remember to put your phones on vibrate. Thanks.
Hi there, everybody. This is Shell on Earth. There's a $ in the title. It's a shout out to all the Unix users out there, which is everyone now because Windows has Bash. And to all the non-technical people, they ask why you have a $ in your title. It's because it makes your talk more baller with the S instead of the $ instead of the S. So today we're going to be talking about the Pwn contest evolution, history of Pwn remote browser to kernel exploits, the full attack chains of the 8 winning submissions of Pwn this year, and then we will conclude. So my name is Matt Malinyawe. I'm a security researcher for the Zero Day Initiative. In my spare time, I was a 2-time United States finalist competition DJ. And that's what I do for fun. And that's why my Twitter handle is DJ Manila Ice. So I'm also playing the DEF CON party later in the week. So come check it out.
Hello, my name is Abdul. I'm a security researcher working for the ZDI. I've been working for the ZDI for the past 3 years. Of course, ZDI, which is part of Trend Micro's Tipping Point. I do a lot of bug discovery and root cause analysis. Jason.
Hey, I'm Jazel Spellman, more commonly known as Wandering Glitch, and I'm also with ZDI. I've been with ZDI since 2012. Tried and focused mostly on reverse engineering and static analysis. And in my free time, I like to play instruments and go rock climbing.
So if you haven't heard of Trend Micro's Zero Day Initiative, we're the world's largest vendor-agnostic bug bounty program. We're focused on vulnerability discovery and remediation, and we do research into advanced exploitation techniques. Also note, we are #1 in vulnerabilities and CVEs at Microsoft and Adobe for 2015. Now we'll go into the evolution of exploit development at Pwn. So prior to Pwn 2013, these were some of the exploit mitigations that were available to the applications that were put to the test. Basically, things weren't easy during those times. They're pretty hard. When I got started probably 5-6 years ago, that's a lot to catch up with and try and bypass. But in 2013, we made a significant change to the Pwn competition where we required the full exploit chain and details around the vulnerabilities to be disclosed. We also made much higher payouts to the winning exploit chains to reward all the vulnerability researchers that participate in the competition. Each affected vendor receives a copy of the exploit chain at the contest and are given an opportunity to ask questions from the contestant in order to improve their software. So it's a real positive thing, and I'm a big fan of it. So now let's take a look at some of the exploit mitigations that have arisen from the change. Here we can see some of the important exploit mitigations that have been developed, and details around the exploit techniques and the vulnerabilities have definitely made a clear impact into people's software and has influenced the increase of defensive technologies being developed today. And here's a slide that shows basically our Hall of Fame of folks that have produced remote browser to super user exploit. They've bypassed pretty much all the things I had discussed in the prior 2 slides, and it's a tall order, and we're really proud of these guys. So you have John and Nils, you got Sebastian and Andreas. All these are great guys, by the way. The Keen team, Mario Smolinski, by the way, his system escalation bug is probably the most hilarious bug at Poneon of all time, because he was able to use the EMET installer to uninstall EMET, and as a result, get system with it. That's super wild. Who does that, man? And of course, our big winner, 2015, Jung-Hyun Lee, who holds the single biggest payout in Poneon history. As you can see, year after year, this type of activity where you're escalating from browser remote code execution to highest privilege is increasing. And the exploit mitigations are getting bypassed and sidestepped altogether by these elite few. But this is a really good thing because the defense gets better and we make things better. Now let's go into this year's Shell on Earth exploit chains at Poneon 2016. So now we'll be discussing the Safari chain produced by Team Shield of Tencent Keenlab. And let's start with some shells. How about that, everybody? All right, so the VM on the left is the target machine, and the VM on the right is the pwn serving machine. It's sending a dilib to get thrown into the browser to execute the privilege escalation. And then there's the shell over there, and it's running as root. And to prove they definitely got root shell and can do stuff, they wrote to the root pwned by Keenlab. So now let's talk about the chain. The Apple graphics context UAF. This was a use after free with graphics context object. This caused execution to die at set platform text drawing mode, as you can see on the slide. If you look at the pseudocode, it's controlling the this pointer if you're able to reclaim the object in time. When you're doing use after free exploitation, you want to know who created the object, who freed it, and which part of your script is reusing it. So basically, a lot of this stuff was happening during a fill text function call. And the free was occurring, let's see. The free was occurring with a modification to the width attribute of this this canvas object. It was basically resetting the size to it. And then when you change the width, it goes and deletes the old one. So basically, if you reclaim this, you could do more interesting things downstream. So let's discuss the exploitation steps. So after they reclaimed the freed memory, they found this exploit primitive with the save function within graphics context save. And that's what gave them the arbitrary write. They sprayed the memory with strings and frame objects, as you can see. And that's the memory layout. And they were able to use that write primitive to overwrite the string's length attribute so they can read large chunks of memory, however they really wanted to. And then they read in the frame view table pointer to bypass ASLR. Finally, they used the write again to write the view table of the frame object pointer and then called the blur function on it so that they can get code execution. So long story short, with multiple usages of this write primitive, you can do cool stuff. Now let's talk about the escalation. The bug was in the multi-touch support binary. And if you look at V2 in this slide here, let's say that's a CF data object. If you're able to reclaim that by kicking off the thread and winning this race condition, you'll get to do more interesting things downstream. So here's a race condition details. It's invoked by calling xset global force config, which resides in core graphics inside the Windows Server process on OS X. And shortly after the call to this function, this unserialized gesture configuration function, there's another call to CF release. So if you reclaim it in time and you get this CF release called on the data that you control, you can make a dereference on the method call of objects. It's the Objective C stuff, but Object C message send when the CF release is called, and that's how they got direct code execution. Oh man, this is a lot. So yeah, basically with this slide, don't let it intimidate you. They basically called the Windows server to get the connection port to be able to call their the vulnerable function. They sprayed memory and they win the race, and then you hit the ROP chain by hitting your stack pivot and then run your shellcode. And if you're running in the Windows server, you're running as the Windows server user, but all you have to do is basically call set UID 0 and then your root. So that was it. Next exploit chain is Apple Safari, produced by Team Sniper of Tencent Keen Lab. Let's kick off this demo. So a lot of this stuff is being discussed right now and concurrently with Keen Lab in another talk. So we're just going to go over higher level how this worked. Basically, they had a vulnerability in JavaScript core, able to get a use after free. And after that, they're able to read whatever they want to because they controlled the toString function, so they could read all the memory. And since you're executing in JavaScript, well, it's executable, and they can redefine the toString function, and that's pretty much it. So the layout was exactly this. Oops. The layout was basically the exact same. Sprayed string objects, frame objects, and then just code exec. And that's pretty much it for the chain. So the details of the kernel portion are being discussed right now. It's in the Apple Graphics display driver code. The next chain we're going to be discussing is Apple Safari to kernel by LokiHard. And we'll kick off this demo. So this was composed of a use after free within the renderer process, heap buffer overflow within the font process, sandbox escape to be able to escape the sandbox process, and then a logic error to execute to escalate privileges with the sudo command, which is very interesting. So you can see here, there's the shell, and do an ID, you'll see the root and the root. So popping calc, popping shells, that's pretty cool. All right, so this was found by source code auditing. LokiHard, Junghoon Lee, pointed straight to the WebKit source code where this use after free was occurring. In this case, he noted that if MQs is null and only M regions exist, set track 0 on the items in M regions never gets called. So after that, you got your dangling pointer, start reclaiming. So the exploitation steps go as so. He leaked a heap address off of a list object within M regions. He sprayed a series of string objects allocated around the track element. He leaked arbitrary addresses with the mode attribute with the associated track element. Then he sprayed array buffer objects around and corrupted the aforementioned list attribute, which is that VTT region list object, and achieved the right primitive, allowing for out-of-bounds read and write access. Finally, this is a ROP-less execution because it's happening within JavaScript. He basically was able to get runtime evaluation by dropping a shellcode into a JavaScript function, having it be evaluated, and then rewiring it to be called with the onQueue change function within the reclaimed object. So now we'll talk about more privilege escalation. FontD has a XPC, which is font object server, so you can communicate to this via that name. And if you send a hex TUE message to reach this function, which allocates memory of the size that it reads from the controlled data, the control pointer, it'll get passed down into get uncompressed bitmap representation. Get uncompressed bitmap representation contains no bounds checking, and as a result, you get data copied into the buffer, resulting in a heap buffer overflow. So he exploited this by spraying with mock message, and then he triggered the heap buffer overflow. And then he was able to leak addresses because he's already executing, and he can get the addresses of the modules that are already loaded into memory. And then he built his ROP chain and then called mprotect to mark stuff executable, and that's how he gained code exec. The OSX font D sandbox escape was found by looking at this file, which is the font D internal SB file, which is located in user share sandbox. He found that font validator was not sandbox, and after looking at the binary, he saw that the environment variable XT framework resources path could be changed, and he changed that so that it would point to load a module that he controlled and run his code that way. So basically is an environment variable problem, and the stuff not running sandboxed. So finally, he took a look at the diagnostic binary that's on the system. He was able to create arbitrary directories with this. This binary has a method that reads values from the diagnostic messages history plist file. And if you supply a key, submit to local folder with the value of a directory, you will get an arbitrary directory created for you. So how to use this? He basically create his directory at var db sudo, and with the username of the guy that's running, and it makes an updated directory modified time, and basically that modified time is checked by the sudo binary, and if it's within a certain time range, you don't have to type in the password, and then if you can run sudo, well, you get your sandwich, and that's how that works. And yeah, you get to do great things. So I'll turn it over to Jazel. He's going to talk about Chrome.
So really the only Chrome entry we had was from 360 Vulkan, and this one was actually a little bit more drama-filled than any of the other entries. It consists of 4 different bugs. It starts off with a Chrome out-of-bounds vulnerability, followed by 2 flash use after freeze, and then finally a kernel use after free. Here you can see they're running a Notepad as system, at least should be able to see. This kernel vulnerability, as well as all the other Windows kernel vulnerabilities from all the researchers, they all stole the system token by iterating through the process list in kernel land, and then finding the system process with the PID4, taking that and then applying it to the current process. The Google Chrome vulnerability is especially interesting in that it was found and reported just 3 days prior to Pwn to Own. So in 2015, we introduced a change to the rules where we would consult with the vendors, and if they found that they already knew about the vulnerability, we would treat that part of the chain as a partial. So this actually got treated as a partial. What's interesting is Google gave us a Chromium bug ID. And if you look at that, it was duped against another bug ID that is now credited to KeenLab. So KeenLab killed a bug that 360 Vulkan was planning on using, or did use. And that's just quite interesting. The vulnerability itself is in iterate elements. And the issue is in an assumption that accessing elements of an array is safe. They knew that accessing elements of other objects is unsafe, and so they had an explicit check to make sure that they were not acting on any other type of object. But array accesses was actually not as safe as they thought, in that you could add a custom accessor method, a getter method, that would execute whenever you access any given element. Looking at it in code, this is a proof of concept that will trigger the vulnerability. The interesting thing to note is evil callback here. This function will change the length of the array that's being acted upon. And as a result, it'll free the old storage, so you're now acting on freed memory. Then you apply it to the array prototype by calling define getter, and you just set it for any index. In this case, it's setting it to 0, but it could be anything. The third portion of this proof of concept is just filling in the array so it has some elements that are legitimately going to be acted upon. And then you call array.concat, which will trigger the call to iterate elements. And as a result, you end up going in this case, with an array of size of 4. And you go in and you then continue acting on 4 elements that don't actually exist. As far as exploiting this, 360 Vulkan allocated an array buffer object in the freed storage and used this to craft a custom array buffer object that had a size that they were able to control. And they used this to get arbitrary reads and writes. One of the key portions of this part of the chain was leaking the address of kernel 32. And they did this by leaking the address of a text object, then using the arbitrary reads and writes, they used that to get the address of Chrome DLL. Once they had the address of Chrome DLL, they used that to parse the import address table and find kernel 32. Once they had that, they then triggered the flash portion of their exploit chain. The first part is a use after free in the handling of ActionScript 2 transform objects. This vulnerability is solely used as an information leak, and that's all it really can be used for. The issue is that transform objects contain a matrix property, which is just an instance of the matrix class. And whenever you access transform.matrix, the matrix property of any transform object, it will create a new instance of the matrix class. The issue specifically is that ActionScript 2 is very, very lenient. And when you access the matrix class, you can actually trigger user-defined code if you hook flash.geom and add a custom accessor method. Another thing here is ActionScript 2 is very lenient, and as a result, you can bind it to a matrix and allocate another object. So you'll get object addresses as a result of just reading what should have been there. The proof of concept here is fairly straightforward. We can ignore the first part. It's basically just getting a movie clip and getting a transform object that we'll access. The second part is getting access to the geom object namespace that gets modified. After that is saving an original reference to the original matrix, because that has to be returned so that you can actually continue code execution properly. The most interesting part is the third part of the proof of concept, where they're adding the property to the matrix, to the geom object. And here, in this case, they're removing the object and then just removing the movie clip and then returning the original matrix. In the actual exploit, they replace it with a custom object that they're choosing so that they can then use it in the second flash vulnerability. So all in all, to exploit this, they triggered the vulnerability. Then within the custom accessor, between freeing the movie clip and returning the original, they allocated a bunch of custom objects. And then they just read the values back from the matrix property and used that to know exactly where in memory their custom objects were allocated. The second flash vulnerability and the last part of the userland chain is in the handling of the loadvars object. It's used after free and also in ActionScript 2. Loadvars contains a decode method, which is used to take URL encoded strings and use that to set properties on an object. So if you have a string that says A equals 1, ampersand B equals 2, and you apply it on a object, it'll set it so that object.A is 1 and object.B is 2. The whole issue here is one of the properties that's built into to ActionScript, actually ECMAScript in general, is object.watch, which allows you to set a callback that will fire whenever any property is modified. And as a result, you can modify and free movie clips and replace the object and get use after free. Once again, here is the proof of concept, and just as with the previous one, the first portion is not too interesting. It's just setting up the variables that we'll be using. The interesting part is really in the second portion where you're calling mc.watch, setting it on AAA. So when AAA is set or modified, this function will run. And in this case, they're only removing the movie clip, but for the full exploit, they reclaim that memory by allocating their custom objects. The last part is where you're actually triggering the call. Now, note that myLV, that the load vars object has its decode method called, but it's actually being applied so that the properties are set on the movie clip. This is required for the actual exploit. Otherwise, the use after free would not actually occur because it would not be writing to the movie clip object. So triggering the vulnerability is part of setting the property. A dynamic call occurs, an indirect call. To bypass that, the kernel 32 information leak is used so that you can actually return cleanly and continue things on for the rest of the exploit. As part of reclaiming the memory, they were able to achieve a arbitrary address decrement. And although this is limited, because they have the information leak from the first flash vulnerability, they use this to decrement the reference count and replace that object with a custom object or with a byte array. So now they have two objects pointing to the same address. And they have the byte array, which has sizes and positions, and they have their custom object. Using the custom object, they're able to change the size such that it is much, much larger than it actually is. And they're able to read and write through basically all of memory just by updating position and reading and writing. The kernel portion of the chain was a use after free in surface objects. This arises due to the fact that window objects are created and handled by the Win32k subsystem, but all surface objects and related objects are handled by the desktop window manager, dwm.exe. As a result of some mishandling of reference counts, it was possible to get a compatible DC object to have its reference count messed up, and it was not properly tracking things. So a surface object would end up getting freed, even though it was safe, but the associated compatible device context object would not be. So you'd have a dangling pointer that you could abuse. One issue with this is cleanup is vital. As part of process termination, process death involves the cleanup of all these objects. And if you don't clean things up properly after exploitation or just in general, then it would cause a blue screen and the entire system would shut down. Exploitation was about standard for the 360 chains. It was reclaim the object with accelerator table objects and then bitmap objects, and then use the bitmap objects to achieve arbitrary read and write access. And as I said when I was showing the video, they use this to iterate through the process list and steal the system token and apply it to the current process. So now I'm going to go over the Adobe Flash chain from 360. This is the pure Flash entry. The previous was solely Chrome, even though it did have two Flash vulnerabilities. So here's the proof of concept itself. This starts off with a Flash type confusion vulnerability and then leads to a kernel use after free. The type confusion vulnerability is used for first an information leak and then an arbitrary use after free. And the kernel use after free is used basically just to get arbitrary read and write access. So once again, they have Notepad running as system. The issue here is in the handling of net connection objects. Net connection objects in ActionScript 2 are a little bit different than your typical objects. All ActionScript 2 script objects contain a type ID as well as private data that is specific to the type ID. Typically, objects have their type ID and their private data set at the same time, but net connection objects have them set as part of establishing a connection. The secondary issue that's just inherent to ActionScript 2 and actually JavaScript, ECMAScript in general, is implicit type conversions, where if you try to treat something as a object type that it's not, it'll try and convert it to the type you'd actually like it to. And if that fails, okay, but it does offer an opportunity for executing code that may not have been expected or intended. This is the proof of concept. We're actually looking at it. It's probably easiest to start bottom and then look up. So net connection is called, net connections connect function is called, but before that, it's passed a XML object. This XML object has a custom attribute that is set. The attribute name is irrelevant, but the important thing is that it's being set to this O object. And this O object has a custom toString function. The toString function is calling super and then returning a string. Calling super ends up in calling the super constructor for net connection such that it sets the type ID. But by allocating color matrix filter objects, they're able to confuse color matrix filter objects as a net connection object. The reason they chose this is that color matrix filter objects contain an array of 20 floats that can be read and written. And using this, they're able to leak a pointer to a string, specifically the string that contains the URL that's used for the net connection. And then they write to it and modify that pointer such that they now have the ability to trigger an arbitrary use after free. They use this to create to craft a modified byte array object that has a custom length. And once they have that, they have read and write access to basically all of userland memory. And at that point, code execution is fairly straightforward. The kernel portion is a window use after free arising from userland callbacks. This is an area that has been hit up quite a bit and still is apparently occurring. The specific issue is in when XXX end defer window pause X calls post IAM shell hook message X. The issue is that they're only using an HWind handle to a window, which is generally safe, but post IAM shell hook message X does not actually do any verification of the handle it's given. It assumes it's still valid, and it's kind of hard to see here, but A3 is the window handle, and it is just directly offsetting into the pointer in gshared info. Typically, you would make sure it's still valid by contacting the handle manager and or calling validate HWind, but they were not doing that, and as a result, there was no incrementing of reference count or any validation whatsoever. Here we can see a snippet from XXX end for Windows position X, and there's no validation. In this case, it's a V52. They're just verifying that a window handle was actually passed, and outside of that, they call it directly with no maintenance of the reference count. Exploitation of this was the exact same as the Chrome chain, where they allocate accelerator tables on top of the now freed window object and then allocate bitmap objects adjacently. They use the first bitmap object to update pointers in the second so that they can just call get bitmap bits and set bitmap bits to achieve arbitrary reads and writes. And then like the previous chain, they just iterate through the process list and steal the token. This is Team Sniper's flash chain. This starts off with a flash stack overflow and then leads into kernel land with a kernel pointer information leak and then a kernel use after free. And then here they have a command shell that is running as system. So the interesting thing here is this was found as a result of a Project Zero vulnerability. Project Zero found a vulnerability in the JPEG parsing, JPEG XR parsing in Adobe Flash. Although Adobe Flash does not release source code, they have a JPEG XR parser that very, very closely matches the ITU reference implementation. And Stephen Vito of Project Zero found a vulnerability and published it. But for whatever reason, neither he nor Adobe managed to see that the same vulnerability existed in the else condition. It's actually slightly different, but it's effectively the exact same, where in this case, RL coefs is an array of user-defined, user-supplied values, and I is supposed to be an index that is supposed to be less than 16, but because it's user-supplied and there's no validation, or no real validation, they're able to access out of bounds and achieve reads and writes. Looking at adaptive LP scan, we can see that they do have a check. A3 is I in this case. And the only check they're doing is to make sure that the value when treated as a signed integer is greater than 0. An interesting thing is, for whatever reason, in the Flash debug builds, not only was there this check, but there was an explicit check that, in addition to this, also checked to make sure A3 was greater than 15, and in both cases, it would still allow this, this code path to be hit and still allow the writes to occur. I don't know why that was the case, but it was. So as far as exploiting, the vulnerability was actually triggered several times. The first time was just to leak a stack address, which was used to craft a fake object pointer. And they triggered another time to leak some more pointers. And then once they had that, they made a function call in ActionScript where they are calling the function with over 100 arguments. It's all the exact same fake object. And the whole point of this was to update pointers within the second object, and then use the other object to perform arbitrary reads and writes. And once they had that, they just wrote to the stack, and they just wrote their ROP directly to the stack so that they were able to return and code execution happened. It was a very clean exploit. The kernel portion starts off by allocating a PFF object, which is basically just a font. It's a representation of a font. The information leak is effectively a logic issue where this function, ntgdi get env UFI, would call another function, gre get UFI, and it's supposed to return an ID that is used to reference the PFF object. But for whatever reason, they forgot or didn't check, and they were returning the kernel pointer. So you had a direct kernel pointer that was being leaked to userland of a font that you had some control over. The actual exploitation from kernel land occurs as a result of this function, bdelete loadref, which is used as part of cleaning up a font. Specifically, it's used to free resources associated with the PFF object. But the issue here is the return code was very dependent on the reference count. So if the PFF object still had any references to it, then this bottom check would fail and it would just return 0, even though it may have actually freed the associated objects. So you'd have a PFF object that has stale pointers to objects that can be reclaimed. And as a result, the caller wouldn't necessarily know if the resources were freed. Exploiting this vulnerability occurs by freeing the associated resources and then calling nt-user convert memhandle, which is an undocumented but heavily used function which allocates memory of user-controlled size and user-controlled data. This resulted in a primitive that is kind of limited, actually fairly limited, where all you could do is OR an arbitrary value with 2. But what Keenlab did is they used this to increment or to massively increase the size of a window object's extra byte size. So window objects have pointers to the window text, to their associated class, stuff like that. But in addition, you can have data that's specific to a given window, and that's controlled by the extra byte size. They use this to call setWindowLong pointer to modify the text pointer in an adjacent window. And then they just made calls to internal get window text and nt-user def set text to read and write memory, and then use the exact same trick of iterating through the process list and sealing a token to get code execution. And now I'm going to hand it over to Abdullah.
Right. So before going through the chains, it's worth noting that the edge bugs that we got in Pwn2Own were found by auditing the source code of Chakra, which is interesting. Both edge bugs from Loki and from Keen Team. So I'm going to be covering the Loki's chain here. I'm going to play a small video. So basically exploited 2 bugs, one in edge. The edge bug is an uninitialized variable bug in the concat JavaScript function. And there's another bug that he exploited to escape privileges, which was a traversal bug, which allowed him to load the DLL into like forcing that service to load the DLL and execute code as system. So as the video shows, he was able to pop CMD and gain system privileges. All right. So when concat is executed from JavaScript, basically in Chakra, the code flow reaches concat args. And as you guys can see, the sub item is defined on the stack, but it's not initialized. And inside the loop, if has item succeeds and get item fails, basically it's going to push an uninitialized sub item inside the array, and that's the root cause of the bug. just plain simple. So as for the POC, so basically he defined a proxy trap for the has method and make it return true, and then set that proxy on an array object, and then just call concat, and that's a simple trigger. As for exploiting the bug, in principle, like after the introduction of FunGC, use after free exploitation got really harder. So he used a technique called misaligned reference. Basically, in principle, what he did is he allocated a bunch of objects and then grabbed reference for one of these objects and then forced a free, allocated smaller objects in a way that they will be misaligned against the original ones, and then used that to leak and do a bunch of stuff. So this is the outcome of the spray. Basically, as you guys can see, the date objects were freed, and then you have the data. When they were freed, he allocated data view objects instead. So the reference that he held against one of the date objects basically points to offset 30 of the data view, and offset 30 basically contains byte offset and data, and these will so basically the reference would treat the byte offset and the data as vtable and type. Respectively. So that's how he was able to leak memory. So as for achieving read writes, so what he did is he basically freed the data view objects and then allocated a bunch of native float arrays. And then he used a fake data view to achieve read and write. As for CFG, he used a set jump call just to obtain the stack address and override the return address, which was simple. So now I'm going to discuss the escalation piece. So as I mentioned before, it's a traversal bug. There's a service called the Diagnostics Hub Standard Collector service. It's a long name. So basically what it does is it captures events in real time and processes them. It exposes a COM interface. This COM interface basically exposes a method called add agent. And the add agent method takes two arguments. The first argument is a DLL path, and the second is a GUID. This method doesn't really do proper checking on the path, so as a result, it can end up loading DLLs from undesired path, basically. So this is a snapshot from IDA just to show the load library call. There isn't much interesting things going on before that. Just doesn't check the path properly and then just loads the DLL. And that's how we got the system execution. So the next chain I'm going to be discussing is Keen-Lab Edge 2 system. So this is a small video. They exploited two bugs too, one in Edge in the fill JavaScript method. Which is an out-of-bound access, and they also exploited the buffer overflow in the DirectX graphics kernel driver. So in the demo here, they were able to steal a system token and modify the Edge token with that token. So so now the Edge process would show that it's running an under system. All right, so when calling the fill JavaScript method in Chakra, the execution flow reaches, it starts from entry fill. So in entry fill, what happens is it fetches the length of the array from the length property, but it doesn't really fetch it from the internal slot. So in specific cases, the length property can be overwritten. Later on, the flow reaches fill helper. So basically, since the length can be overwritten, and then like out-of-bound access can happen, and that happens specifically in direct set item. But the bug goes a little bit deeper than that. So since we're dealing with typed arrays, the execution flow reaches base type direct set item, and basically what it takes the index and what happens here, it actually checks for if the index is less than the actual length, which is from the internal slot, but it does it through an assert message, and it just logs the message, and later on it just writes whatever to whatever index we specify. So that's the actual bug. The POC is simple as well. So basically, just define a typed array and then set the prototype to another array, specifying whatever size, and that's where the actual length property override happens, and then just call fill. As for exploitation, the exploitation technique that they used was just composed of corrupting the length of a JavaScript native int array. In their exploit, they used two sprays. The first spray was used to stabilize the heap, and the next spray was used to fetch the index of one of the objects they were able to write to. So once that's done, once they actually get the index of the target object, they corrupted the length, and that's how they were able to achieve read and write. As for CFG, they use the same trick as Loki, which is calling setJump. All right, so I'm going to go over the kernel buffer overflow. So basically, DirectX graphics kernel driver, it contains a structure called the present history token, and inside that structure, there's another structure called the dirty regions. Dirty regions contains the numrects, and it contains a static array of rects. So in one of the methods, in one of the functions, there's a bunch of cases. One of the cases, which is interesting, is that it checks if the numrects is smaller than the maximum number of rects. So in the specific code there, if the check fails and then it just logs it, but what happens? It logs and it continues execution. So the execution reaches a memmove call, and that's where the actual buffer overflow happens. So we're a little bit running out of time, so apologies guys, I'm gonna go through this really fast. So as of exploited, I'm just gonna go over some details. So that driver basically allocates a pool. Inside that pool, it allocates records. These records are connected to each other as linked lists. So they triggered the bug to overwrite a subsequent record, and then they used a bitmap spray where they were also able to grab a reference to one of the bitmaps and achieve read and write through set bitmap bits and get bitmap bits. And then they were able to steal a system token and just modify the edge token. So Matt, you want to close this?
So we're going to conclude here, and big takeaways is application sandboxing is a step in the right direction, but the kernel attack surface remains expansive and exposed. Basically, the return on investment of learning a code base in the kernel will net you higher privileges, and it's probably a good time invested. Exploitation is getting harder, but still very possible. Write exploit primitives are a mainstay in exploits. You know, if you got it right, you could probably install Doom in like your browser if you wanted to, or write your own exploit mitigation. You know, you could write, so you could do whatever you want, right? Another takeaway is logic bugs can be very high impact, as we saw with the pseudo bug and the directory traversal bugs. And vulnerability exploit research is becoming increasingly popular. We see a lot of new faces every year at Pwn. I like the new breed. They've set a new standard with what they accomplish this year. Basically, they're humble, they work hard, and the work talks for itself. So it's also becoming a team sport because with the various subsystems that exploit developers need to understand, you're going to have to go to various subject matter experts to be able to develop the code and be able to execute. So exploitation is getting harder, and you know, that's what's happening. So we're kind of running low on time. If there's any questions, we can take some outside. We're the Zero Day Initiative. We have a vulnerability bug bounty program, and send us your stuff. We'll handsomely reward you. So we're also hiring too. So thank you. Thank you.